quickly start today. I came a bit early with the purpose of finishing off a segment which I need to do it today itself, and most probably we are going to solve a numerical if today permits, time permits, we are going to do today, or we'll continue that on Friday's class as well. Because this happens to be the core of AES, which we were discussing for the time being, and that will need a little bit of time to understand, to make you understand, as well as to illustrate the examples also. So, if you remember, we were discussing AES, and in terms of AES, why we are discussing this? Because this is as we have discussed that DES, when we had discussed, we had some issues with respect to the key size of 56 bits, which happens to be going around with 128 bits for the AES. And another thing that was highlighted for AES was that there were different sets of rounds. That means we have 10 rounds over here. Maybe you can mention 10 rounds, 12 rounds, and 14 rounds. And instead of the fixed rounds in case of DES. And where we actually stand at this point is that we have discussed the basic block structure. And in that, we have observed that after the initial permutation, where we are calling that as a pre-round transformation, there are a number of rounds which will go till NR. Now, that NR is ideally as 10 or 12 or 14, as given over here. And based on that, we will have different sets of keys. And the key length will also be 190, 128, 192, or 256. But whatever be the key length, finally the round key, which we are going to discuss today, in fact, will be of 128 bits, and the plain text will also be of 128 bits. And one of the advantage of this was that unlike the DES, where we were using a function to make the left and right bits appear, then we had a use to have a swapper in between. Nothing will happen over here, except there are 4 transformations that will take place. Alright, so today's discussion is primarily based on these transformations, because all these transformations are happening for every round except for the last round, which is round NR. As I said, in case of AES, the mixing round, which we'll discuss today, will not be present in the last round, except for all the round it will be present. But if you go to the detail of it, if I go by the details of each round, there are ideally 4 states which we come across. Okay, so this is where we come across, and in fact, if you remember on last day's class, I told you some definition. That's what you mean by a state. A state is nothing but the intermediate status of the data bits. And remember, in AES, most of the things we are discussing in terms of bytes. Alright, so it was a 4x4 byte or the 16 byte matrix which we were talking about. And based on that, if you remember, I think I'll not repeat it again, but still, just because there is a lot of gap between the last class and today's class. So if you remember, we were discussing something in terms of words. And words were nothing but, if I consider array, I think we don't have, I don't think we have a diagram here, but maybe I'll just show you here that suppose this is my array of the 4x4. So each of this column will indicate one word. So this will be one word, this will be word 1, this will be word 2, and the final will be word 3. So this the first 4 words will be generated automatically by the key generation algorithm. But after that, there will be something called as key expansion technique, in which these 4 words will give rise to 43 more, or rather 39 more words, which will be used as a key for the plain text. Now today we are going to discuss about the expansion algorithm along with the process that is involved over here. Now the one that you are looking at over here, this parts, okay, so this is my state. So this 4 things that you are looking at, shift rows, sub bytes, shift rows, mix column, and add round key. So these 4 are the transformation that an AES round, each round will undergo. If I go back to the previous diagram, if you check here, this is present over here. So this is my shift, not this one. This is my sub bytes. This is my shift row. This is my mix column, and this is my add key. Alright, so we are going to discuss this 4 status, 4 transformation after this is my pre-multiplication, or what we call it, the heading is pre-round transformation. So this is my pre-round transformation. So after that, all these 4 transformation will happen for every round. Now, what are these elements? Okay, so that's what the discussion is. So this is my primary diagram. So first operation that it goes through is the sub bytes. So let's see what exactly is sub bytes. So this is what we are discussing, sub bytes. Now usually the sub bytes is a process in which what happens is that suppose this is my state. I'll give you an example after this. So suppose this is my state and we have the column matrix or whatever the elements. Now each of these bytes, now if you check this one, we have shaded this particular byte, suppose. This will be checked with a table. Now this table is a standard table associated with AES. I'll show you the table also. So for encryption there will be one table, for decryption there will be another table. Now what will happen, for every byte we will see the inputs because they are all hexadecimal numbers. So we will suppose we are getting a value of 02. Suppose this element has a 02 entry, for example. So what will happen is that this 0 will indicate the row of the table, and please make a note of this, and this will be giving us the column of the table. So the entries to each and every byte of the state matrix, when we are undergoing the sub byte setup, each of the byte will have the corresponding nomenclature, where the first bit will be, for the first byte will be considered as the row number and the second one will be considered as the column number. So let's see. So each and every case this substitution will take place. So let's see with an example. So this is basically the table. If you observe here, the table that is given, it starts from 0 and it ends at hexadecimal number F. Whereas in the row also it starts with 0 and it ends at hexadecimal number F. Now this entry that you are looking at, this is a standard table which you should be following all throughout. Now the point is what I made over here, that suppose I have the entry 0, 2. So 0 is here, row number, 2 is over here. So wherever they will intersect, this 77 will be replaced in terms of that particular statement. So if you check this particular example, I have an example over here to show you this. So just observe here, we have 00 as the entry, right? This is my table. I have given it in a short form so that you can at least have a reference. So why 0 is here and my 0 is over here. So my entry is 63. So the sub byte transformation will make the 00 entry to be 63. Simple as that. It is very similar to the permutation that we have done in DES. Similar tables were there in DES as well. So here also we are doing the same. Just take another example. For example, 1, 2. So 1 is here, 2 is over here. Wherever they will intersect is C9. So we have C9. Clear with this? So given any random 4 cross 4 matrix, which we are calling as a state in terms of AES, we can use the matrix or we can use the table in transforming the data bytes from whatever we had as an input. So all these 4 cross 4, 16 elements has been converted to something of this nature. Am I okay with this? So this is the first step of every round. Whenever the plain text is entering, it is divided into or it is arranged into some kind of a state matrix or a state array, and each of those array will undergo through some kind of a table, and every entry of the table will be replaced by this process to make a new table. So this will be my next state. Maybe I call this as a state prime. Okay, but this will happen for every round. Am I clear? Inverse table will also be there. I think inverse table we have here. This is the inverse table. Same way, it's the same process is adopted, but this is at the receiver end. If you are at the receiver end and you want to do the other way around, you come back to the data, then the same thing will happen, state prime to state. Suppose you are doing the other way conversion, you have to follow this table and you have to get back the result. Again, this is a standard table, we cannot deviate from it. So this is for the inverse table, this is for the normal table, the encryption table. Alright, so this is the first step that we come across. So this is where we are. So after sub byte, so this state goes to the sub byte, the tabular changes, and we are right now over here. So the next operation that comes in is called as shift rows. Any doubt with the first one? Any doubt? Alright. Now we come to shift rows, which is also equally very simple. But the process again, it's a repetitive process for every cases. Shift rows is a process which follows something like this. Just follow this carefully, because again, it's a very easy way to understand. But if you don't remember the process, it might create a problem. The process of shift row is, for all these cases, again, we have received a 4x4 matrix, right? After the sub bytes have gone through. So please see the rule. The row 0 will remain unchanged. Row 0 of the initial input will remain unchanged. Row 1 will have 1 byte of shift. Row 2 will have 2 bytes of shift. And row 3 will have a 3 bytes of shift. Which means something like this. For example, this is what the state which we have received. State prime. It was there in the previous case. So the first row remains as it is. First row remains as it is. Second row, you can observe the F2, the lower half, the left hand side bit has been converted over here. So there is a shift that has taken place, left shift that has taken place, in which F2 6326. Now these are preceding to F2. Now if you observe this C9 and C9, this will be appended at the back of the second row. Can you see the change that you are looking at? First row remains unchanged. Second row will have 1 byte shift to this and over here. Like F2 has come like this. Then we have C9, C9 to 2 byte shift. This 2 C9 has been appended over here. And the last one has 3 bits, so this 3 bytes have been appended. So the second operation, 2 sub byte, is to have a shift row. But remember, for the row, which row you are in. So based on that, you have to change the process. Here there is no problem with the rounds. Remember in DES we had a problem that there was some round in which there was 1 bit shift. There was some round where there were 2 bit shift. Here there is no such problem. Here every row will have to follow the same rule. Am I clear with this? This is the second operation. So first you are doing the sub byte using the table. You are transforming it to some kind of a random table. That 4x4 state is now undergoing the shift operation and you are rearranging the data set. Right? So we are somewhere in this second segment. So after sub bytes is done, shift rows we are done. Now we come to mixed column. Right? So this is where things might get a little difficult, but just understand this very carefully. Here also the process is simple, but the calculation itself is little tricky. We will solve it with an example later. Now what happens here is the mixed column is that each and every column of the state matrix, for example, here we have collected this particular column. Just one example, okay? So we have a 4x4 column, like 4 columns we have. Every column we are looking at over here. You can see the arrow over here. So this is my column from the state matrix, which will be multiplied by a template, which is a constant template and is given over here. Please see this carefully. What we are trying to do, each of the state matrix, each of the column of the state matrix is multiplied by another 4x4 template, which is given over there. And if you see the template, that also has a specific arrangement, if you see. So that's why you don't need to remember it that much. 02, 01, 01, 03. Second row, if you observe, 3 has gone over here. 3, 2, 1, 1. Again, next one. 1, 3, 2, 1. 1, 1, 3, 2. So basically, there is a shifting that has taken place. But we don't need to bother with the template because this template is standard. So basically, for each and every column, you take that column, you multiply that with this 4x4 template, and whatever the results you are getting, you substitute that to the first element over here, like element wise. Like you can see this column is replaced by this column over here. Can you understand that what we have done? So basically we are trying to, just give me a minute. We are trying to make sure that using this state matrix for this particular column, suppose I name this as column 2, now the new column 2 will have this matrix multiplied with that single column. That is the process. And for that, this constant, for the transmitter side, we have this. And for the receiver side or the decryption side, we will have this. So please make a note of this second one also, but most of the time we are not going to focus on the decryption part as much. So the first table will be mostly used. Okay, the 0 to 1 that you are looking at. And as I said, this is even if you don't have the reference with you, it's very simple. 0 to 1, 1, 3, and that goes on with the left shift for the rest of the entries. So what happens is, so now so mixed column is like that. We'll take a separate question itself to solve this mixed column, because the problem here, what you will find is the multiplication. Because you are observing over here, this 0 to, like this multiplication and this elements over here, they are all hexadecimal numbers. So this is not the simple matrix multiplication that we are talking about. Okay, it's a polynomial arithmetic that we are talking about. So that will take some time to discuss, but we'll see that later. So now I'm discussing the process that is involved. After this we are done, the last step that we come across is add round key. So there are 4 steps. First, you are doing the sub byte, where you have a table and you are transforming the table using the table. You are changing the data. The change state, you are undergoing through a shift operation based on which row you are doing. 1 bit, 2 bit or 3 bit you are changing. Then you are doing the mixed column, where you again have a fixed template of 4 cross 4 matrix, with which you are multiplying each and every column of that state, and the final outcome you are generating, and you are generating a new column or a new matrix for that matter. And finally you come to add round key. Now this add round key is done with respect to the round key. Now this generation of this round key I'll separately discuss. But for the time being, let us assume that we have generated a key. We have 4 keys over there. First keys have been used over here. The W0, W1, W2 and W3 has already been used over here. So this is where we are actually using W4, W5, W6 and W7. But how do we generate these keys? I will discuss separately. But suppose, for example, we have those 4 keys. So what will happen? The process will undergo something like this. How? It will be like, this is the state again. Each and every column will be multiplied by the column for the key as well. So this is my keyword. Remember W0, if I consider anything like W4, so it's a column wise we are looking at. So 4 bytes information. So these are my 4 bytes. So this is my key. So this gets stored by each column that is coming over here. Whatever is the result, that is stored as the new column. So this is my column 2 again. This is my column 2 entries. This is my new column 2, which I call it as column 2 primary. So it still remains a 4 cross 4 matrix, but it has undergone 4 such transformation in between. Unfortunately, we don't have any restriction on number of rounds, or we don't have any other PSL functions or anything of that sort. We don't need any swapper. We don't need any left and right arrangements, nothing like that. Only these 4 operations we have to perform. Right? Any doubt with the 4 operations, why we are doing this? First, we are doing that pre-transformation, which is nothing but a XOR operation. You have W0, W1, W2, W3. You are XORing it with the 128-bit plain text. After that, you are generating that 4 cross 4 byte, like 128-bit is arranged in that state. That state matrix is going through first the sub bytes. If I go back to this, first it goes through sub bytes, where you are having a table, input table. Based on that, you are rearranging the data into a new table. After that table is generated, that becomes your state, this one. After that is generated, that is fed to the next input, which is a shift, where the shifting is taking place with the order that the first row will be remaining unchanged. The 0th row will remain unchanged. The first row will have 1 bit change, left shift. Naturally, your inverse process will have right shift. That is quite obvious. If the shift operation is over here as a left shift, while you are doing the decipher, the same operation will happen, but it will be right shifted. Okay. But as I said, most of the time we will do the encryption mostly, so we don't need to worry much about the decryption as of such, because it's just a reverse process. So then we have the shift operation. So after shift operation, we have mix column, where we are mixing each and every column with a template matrix, and we are generating a new column, and we are arranging new state matrix. That state matrix is fed with the generated key, or the round key we call it, and in the process, each and every column of the state is XORed with the individual 4 bytes of word. Alright, and that's where the final ciphertext will be generated. So this state, the last state that you are, that's where I'm marking. So this is after round 1. Suppose I consider this as round 1. So this will be my round 2 input. Right, and this will be followed all throughout up to the 10th round if we consider the 10th round. Am I clear with this process? Any doubt? Anyone? Because this process is repeated every time. So irrespective of the matrix which is provided to you, it will be repeated again and again. So let's take some examples so that we can understand that. But before that, maybe the most important things that I think I should mention also, that how do I generate the round key? Because that part is missing at this point. Okay, so we'll take that first and then we'll take one by one the example. So this is where we look at something called as key expansions. This follow very, very carefully because this is the heart of our key generation. So if you see this table, I already had shown you in last day's class when we took it on Wednesday. And I told you that the first round, if you observe, this is a pre-round transformation. This W0, W1, W2, W3, these are the first predefined words that we are setting in for the particular time being. First 4 words are generated. But after that, if you observe all the rounds, they have some W4, W6, W7, up to W43 in fact, which are generated by some rule. Now, what is the rule? For that, I need description of this. We don't need to follow this block diagram as such, but this gives us an understanding on how the words are generated. So if you look closely, it's very simple in fact to understand from the fact that how it is generated. So these are my cipher key, which is of W0, W1, the initial W2 and W3. Now, how W4 is generated, if you observe, this is my W4. This is nothing but a XOR operation between a temporary word which is T4. T is a temporary word with W0. So the leftmost bit, W4, W8, W40, all of them are responsible with respect to some kind of a temporary bits. And the rest of the bits are dependent on the previous word. You can see W5 is a combination of W4 and W1. Am I clear with this? So only the leftmost bits are dependent on some kind of a temporary word and the rest of the other words are dependent on the previous word. That's how it is. Okay. Now, if you observe the T, the temporary word, that also is given at the bottom, that how it is generated. How it is generated? We have the Wi minus 1. For example, in this case is W0. Suppose the first one I am considering. So, Wi minus 1. Then we have rot word. Now, this rot word is again a template given to us, provided to us. I'll show you next slide. So, you are getting some kind of a rot word over here. You are drawing that. Then you have something called a sub word, which is nothing but similar to sub bytes. Same thing we are doing. And finally, we are making sure that we have R con. This rot word that you are looking at, okay, this rot word is nothing but a rotational of word. I'll take the example, I'll show you. This is the rotational part, this is the substitute part, and this R con that you are looking at over here, this will have a template, a fixed template. So let me just show you one by one, okay? See this carefully. This table that you are looking at is the prescribed R con template for X. So if you observe round 1, round 2, up to round 10, the table. So for each and every round, when you are generating the round key, if you go back to the previous slide, you need this R con over here. So if you are in round 1, you are generating the round key, you will follow this particular entry. Am I understandable here? I'll go back here. This is my Tj rather. Now how we are generating this? We need the initial word which is W0, which is there from the cipher key. Then suppose we know about rot word and the substitution or sub word, but we are concentrating on this R con. Now this R constant is given by this particular template. So whenever you are in particular round, you are going to use that particular value of constant and you will XOR it with the preceding element. Am I okay with this? So if you observe here, I have already mentioned subword and rot word on wi minus 1 and XORing the result with round constant rcon. That's what we are trying to do. This is only required for the leftmost word. So if you observe over here, the condition for it, so condition is given over here. If I mod of 4 is not equal to 0, then wi is equal to wi minus 1 plus wi minus 4. This I have given you an example over here. Suppose I is equal to 4. Suppose I is equal to 4. So I equal to 4 means 4 mod 4, this is equal to 0. So the first condition doesn't apply. The second condition, if you observe, if I mod of 4 is equal to 0, then wi is t plus wi minus 4. So you can see t plus w omega naught. Now this t is generated by the subword, the rot word, and XORing it with the first round. Suppose this one, this value 0, 1, all zeros. Got it? So this is how the first round of keys will be generated. The first entry, this will be W4. Now when it is W5, for example, I5, this will be a combination of W4 and W1. If you go back here, W4 and W1 is connected. So that is given as a relationship over here. This is a generic relationship. This is a generic relationship. Wi minus 1 plus I minus 4. This is for odd value. And for the even value, we will have so the leftmost entry in general will need a temporary array or temporary key plus the raw R constant or the previous word, and we will generate the key. Confused, I know. I'll take the example and let me show you that how it is done. But are you able to understand the process how it is to be done? We first discussed the transformations of 4 states. At the last, we will require add round key. The process that I am discussing over here is generating that round key. First 4 key is not the problem. We already have those 4 keys. But how does those 4 keys generates the rest 39 keys, at least for 10 rounds? That is what is explained over here. So for that, we will require a constant, R constant, which is given in this table. And for that, we will require the rest of the bits, which follows the relationship as given over there. But in general, intuitive understanding from the diagram suggests that all the leftmost keys will require a temporary key XORed with the previous data. Okay. And the rest of the key will depend on the other 2 words itself. We don't need the temporary key for the other set of words. So let's take a direct example so that your confusion gets a little less and we can understand clearly. So suppose this is the key generated. I'll just go by the just give me 1 minute. I'll just show you that over here. Just follow this carefully. Okay, this is a real example that I will be taking, practical example to understand this key expansion. Now, if you observe, this is the key given. A 128-bit cipher key is given to us. What is the first step? We need to know what is my W0, W1, W2, W3. So from the cipher key, we are dividing that into this particular half. You can observe the step 1. W0 is nothing but we are taking 4 bit at a time, 4 bytes rather at a time. So we are considering W0 and W1, 2, 3 like this. Any doubt in this? So you will be given a set of cipher key. From that, the first step is to divide that into equally 4. This much information is only known to us. The rest of the elements we have to generate one by one. Alright. So now, if we observe that I have already mentioned over here, but let me just go through it once again. So this is my 4 keys. Let me just keep it there. Now see the rot word. Applied only to one row like a shift operation. This is what is happening. You don't need to know the theory. You just need to know the process involved. To be applied only on Wi minus 1, that is W3 in round 1. The W3 is the last word, remember. Okay, so if you are applying it on W3 in round 1, as per the rule, row 1 shift number of bit by 1, byte by 1. So what is my W3? This is my W3. We are just shifting this 13 over here. So this becomes my rot word at that point, because if you observe the template given over here, wi minus 1, wi minus 1. Okay. Now what we are trying to do is, we are first trying to have, we are generating w4. So we are generating here, we are generating, because up to w3 we know. So w4 is what we are generating. So my I is equal to 4. So as per the rule, wi minus 1, so w3 should be considered as the first bit that enters to the rot word. So that's why we have considered w3, and we have shifted only the first byte over here, and we have shifted over here. So this is my intermediate rot word. Next, what was there? Subword. So now let's see the subword. So now this is where we stand. Now we have the table once again. The same table that was used for sub bytes. Same table. Here what we are going to do, for each and every entry we will substitute by with respect to this particular table. So if you observe AA, that's what I mentioned by this. This is a blue colored one. So A is over here. Another A is over here. So A and A meets at AC. So my new key, here it's mentioned already. So let me repeat once again. We are at the process of generating the key. Okay, because we are generating W4. As per W4, the rule is W4 we require a temporary data and the initial data. That is W0. W0 we already know. The process that I am involving here, we are trying to generate the temporary. So the first thing is, we take W3 and we shift by 1 byte. So that is giving us the rot word. After rot word is generated, which in this case is this, we are using the table to find the respective substitute for that particular key. So in that case, AA548713, which is over here, the the rot word, is now substituted to subword of AC 2017 and 17D. See the color combination I have given, that's how we are reading it. Any doubt over here? Any point? Please tell me, because this is the crux of it. For any other key, it will repeat the same thing. So please understand if it is okay. For the rest of the bits, that's not a problem, because for W5, for example, that will be a combination of W4 plus W1. So you are just sorting it. We don't need to worry much there. This is the only problem that you might have to understand. Any doubt over here? I'll do it. So the first step, I go back. So this is my key given. We are dividing the first step as the first 4 words, which we have to know. That's for sure, because those are the default. This is that before the round, pre-transformation we call it. So W0, W1, W2 and W3 we are defining using 4 bytes, because that already we have defined as per the AES rule. Okay, so that is first element. Now, as per our rule, the first thing that we need to do, if I go back to PPT, you observe that if I go to full screen, the T is generated, this T is generated by Wi minus 1. The first entry is Wi minus 1. Now, over here, we are trying to generate W4. So, what is my I? My I is 4. So, my Wi minus 1 is 4 minus 1, 3. That's why we have to consider the W3 key for the analysis. This part is clear. Why we are considering W3? Because we have Wi minus 1 over here, and the I over here that we are trying to do is 4. So that's my W3. So that is why we are considering W3. Now, what is my W3? 13 AA 5487. So we are rewriting that over here. Now, the second operation is we are undergoing a rot word, which is basically a rotation of the word. By what? By 1 byte. How we are doing it? The left byte, the left 13 is shifted over here. So the new status of the word will be AA 5487 and 30. This is the intermediate state. After rot word we are doing. Clear? After rot word, if I go back here, so this is where we are right now. Rot word. After rot word, we have subword. How subwords are generated? For that, we require a table which is same table as that of the sub byte that we had discussed in the transformation. In that, what we are trying to do, we are picking up two bit or 2 byte of information. In that, the left bit is considered to be row. That's why I mentioned row R. And the second one is considered to be the column. So double A. So A lies somewhere here, and the column A lies somewhere here. So wherever it will intersect is AC. So we are replacing double A by AC. 54. 5 is the row, 4 is the column. 5 is the row, 4 is the column. Wherever it intersects, 20. 20. 87. 8 is the row, 8 is the row, 7 is the column, 7 is the column. 17 is where it intersects. 17. Last but not least, 13. 1 is the row, 3 is the column. 1 is the row, 3 is the column. It intersects at 70. 70. Am I clear with this? So this is after the sub word has taken place. So this is my final outcome. Now this should be added. If you go back, this is where we are now. Sub word. At this point we are here. After sub word, what we have to add? We have to add because this is the first round we are talking about. So R con 1. See here the expression. R con I by 4. What is my I? 4. 4 by 4 is 1. So the first entry to that table, see this. So subword is over here. XOR with R con 1. What is my R con 1? This is my R con 1. In PPT also I've shown you. So what is my first entry? So what we have to do is, basically, we have to take this one and take this one and we just XOR. Now I've changed it to binary and I've made a XORing operation, and finally whatever we are getting, AD20177D, if I consider over here, that will be my W4. That will be my W4. So you can see. No, sorry, this will be my T1. Sorry, this will be my T1. So T1 plus W0, if I do it, we are getting the final result as W4. I'll go back to the PPT once again just to show you. So this is this point we are using the sub word of KB. Based on that we are finding we are solving that with the first entry on the table. First entry. Because I by 4. So the first entry will be transferred. The first entry and that entry, this is generating my temporary key. Now if I go back to the diagram, this temporary key will get solved with W0. So that's what I was showing you. So T1 is generated over here. Alright. So that gets XORed again with W0 in order to get W4. So W4, if you are getting XORing this will be my key, W4 key. Okay. Similarly, W8 will also be generated in the same manner. We have to go through the second rot entry. The rot word will happen. The one shift will happen. Then we have to check that key with the table. After the generated output, we have to find out the second entry to the rot table, and then XORing it, we'll get the T2. That T2 will get add up with the W, the previous W, and accordingly we will proceed. But if you observe similarly W5 doesn't require the temporary word. It's just the XORing of W4 and W1. If you go back to the diagram, W5 is here. So W5 is W1 plus W4. So that is shown over here. So W4 is already we know. So this comes here. And W1 we had found out in the very first step. This one, we XOR it and we get the value of W5. So W5, W6 and W7 in the same manner we can generate. In the same manner. So W6, what will it be? Can you tell me? W6 will be, if I go back, W6 is W2 plus W5. W5 is what we have generated over here. So it's like BD 20 E346 XOR with W2. Now what is my W2? W2 is given over here. 31, E2, 12 and 0. So 31, E2, 12 and 0. So this you have to solve. So whatever the output you are getting, that will be my W6. W6 will be fed to W7 to generate to W7, because W7 will be again same thing, W6 plus W3, correct, because that's the only thing left. Whatever the output that, so this W4, 5, 6, 7, this becomes the key for the next round of generation. At that point, if I consider that, suppose we know about W4, W5, W6 and W7. Can anyone tell me, if I need to generate W8, which key we should start off with? W7. Correct. And the process continues. Is it okay? If I go back and if I give you this example, which is given in wrap-up in Verizon, you will find a solution to this in related bytes. This is the transition. These are the keys generated, but how they are generated is not mentioned at all. Finally, these are the output snippets. So the document that I showed you right now, the handwritten one, that is the process that goes in for each and every round, for each and every round keys. So basically that the answer that we got, AD 2017D, 7D. So if you observe, this is where my data comes in. So this was my temporary data. And based on that, we found out the other keys over here. So W4 we generated, W5 we can generate accordingly, 6, 7. So this will be used to find out next key. And it goes on. So this is basically the multiplication process or the expansion process of key. So if I go back few slides back and I show you this, so now the transformations are known to us, or all the 4 transformations: sub bytes, second is shift rows, mixed column. Mixed column we have not discussed yet with an example, but mixed column is a process. Then we are doing the add round key, and the add round key and the generation of the round key is now known to us. How the expansion box is working in generating keys beyond W3. Any doubt at this point? Can you take any random example and you can check it? You can just take this as a reference. When I'll upload it, you just take any of these references, any round. Suppose you take this round, third round. Because third round, this keys W1, 2 that you are looking at, this is your W0, this is your W1, this is your W2, this is your W3. And you apply the same rule which I showed you right now and find out whether you are getting the temporary data of this and the rest of the keys are matching or not. Can you do that? Same process, same thing which will be done. So in an exam also, suppose you are given a similar pattern, you should know the process of finding it out one after the another. Clear? Face doesn't look that promising, but I know that with practice it will be, because this is where you might lose out the track while solving the questions. So please, for the time being, as much as possible, I'll do it next day. As I said, on Friday, I'll try to cope up with a few more examples. But if time permits and if you can do it by tomorrow, we have Thursday, we don't have any classes, at least take one of this example of this W0 and take the process and find out that whether it's matching or not. Okay. Just do that, okay? That's just for your own understanding. Alright? So this is about the key expansion, and I think the other thing that I'm talking about, the multiplication part, I don't think we can start off today because that will take a separate discussion altogether. Let me finish off on that note, okay, with that process, because this repeats because we don't have anything else in AES. We have the initial permutation where we had changing the data. You just take this particular example. Maybe I'll just give you this example to finish this thing off. This is also a given example from Frozen. Now, if you observe, this is what the input side is. This is my input state. That is a plain text, initial state, and this is my initial round key. Now, in case of the pre-transformation, I told you that it's basically a XORing operation. So, what we have is that each of this column is just getting XORed with each of this individual column. So, if you see, this is one of the example. I'm just taken first column itself and you have calculated it. You can see the 24, 71, B0 and A7. This is appearing here. This is same as that of the add round key process. Just the same thing. You take one column, you XOR it with the standard column, and whatever the output, you just substitute that with the new column, as a new column. So that is happening over here. Okay. So, and you can see that this I will check later. So this is basically what the AES process is. Each and every round will have the same, except the last round where we don't have any mixer as such. But before we end up and we take the example separately on Friday's class, let me just show you a few things before we leave out. First thing is that the weakness in key, which you remember in DES, I told you that there is a sufficient amount of weakness in key that if suppose all are zeros, then after a certain period, the keys are going on repeating itself. Remember in DES, the fault in DES, why we have chosen AES. But if you observe here in case of AES, even if we choose all the key W0, W1, W2, W3 as all 0 keys, after 2 rounds, you can see after 2 rounds, all the keys are completely random in nature. So that is the beauty of AES, that even with all 0 keys, with the sufficient algorithm is such that post round 2, you will get all random keys after that. So that is a definitely advantage compared to DES. That is the example given over here. Next is the last one which I can just touch upon is the 192 and 256. These are the two other flavors of AES as I told you. Same process, same thing, except you can see the words are generated in groups of 6. In case of AES 128, we are generating by 4 words. Here it's 6 words. And in case of 256, it will be 8 words. That's the only change. And you can observe the equations also, all are same except that here it is 6. In case of the 128 version, the one that we studied, it was I minus 4. 4 was there because we have considered 4 words. But here as it is 6 words and 8 words, you can observe the end product over here is 8. But the process involved is absolutely the same. Nothing changes. So the key multiplication process or the expansion process, whatever we talk about, is the same. Am I okay with this? So by this we end our discussion on AES with terms of the process. Let's come back on Friday and let's take particularly the mixing of the data, mixing part of it, because that will take a little bit of understanding. Because without the mixing part, if suppose I give you a input status, it's okay to do the sub bytes because you have the table and you can convert that. It's okay to have the shift rows also because you know the process. But this mixing of the data with the matrix, this requires a little bit of skill. So I'll take one single example, two rather example, and I'll show you how the process should be involved. Because post the mixing, only then you can add the add down keys, not prior to that. So the question can be that this is my input, what will be my final output? So you have to make sure that the sub bytes, the shifting, the mixing and the add down keys, all this is taken together to find out the output state. Understand? So that is how the thing should work out. So let us stop at this point. We'll come back on Friday and we also have a class, as I said, on Saturday. So we have some time. So let us see how much example we can set. Because we still have RSA algorithm, which is an asymmetric algorithm, which we are going to discuss.